All right, we've done our review. Now we want to move on to the course itself. These are materials that is actually in Statistics Part 2. The first topic we're going to try to tackle is looking at the difference between two means, two different populations. Each population has a mean. Each population has a standard deviation. To start things off as easy as possible, we're going to assume that we know the standard deviations of the populations. And then, as you can imagine, we'll work from there. But this is so that we know what we're talking about here. We're talking about the easiest case where sigma 1 and sigma 2 are known. A simple example where this might be important is if you were to look at, say, the average age of Democrats versus the average age of Republicans. Each of these groups would be very interested in this information. The numbers that I've written on the screen here, though, are made up. I didn't look them up. But the point of it is that each of those political groups, Republicans or the Democrats, would very much like to know the average age of their people so that they know how to best market towards them and try to get them on board. You market things to elder people in different ways than you market things to young people. And middle-aged people, you market different from any of those groups. So there's a lot of research that's done after you get this information. This tells them probably a lot on how they're going to send out or even do materials for their people. So basically, what we're going to do is look at situations similar to this. We're going to have two groups, two different populations, and it's quite possible that they'll have two different standard deviations. So let me start with some definitions and go from there. Two samples are independent when a sample from one population is not related to a sample from a second population. Otherwise, we say the samples are dependent. As an example to illustrate this, let's say we have the following sample. Let's call this sample 1. What do we have? We take 70 people and measure their blood pressures. Sample 2, the same 70 people, but after they've taken, Benicar is a blood pressure drug. These samples are obviously dependent because people Well, it's the same people in both samples. This is more of a before and after study. So this would be better to do as a one sample thing because we have a before and after. So anyways, these are dependent. There's another example. Sample 1. 100 preschoolers have their IQs measured. Sample 2. 100 retirees have their IQs measured. Now this is assuming I'm doing this at the same time, both samples, so it's clear we can't be preschoolers at the same as being retirees, so they're not connected to each other, so therefore we would consider these to be independent samples. This is just touching the surface. We'll do more on this as I do examples, but let me get into the examples to see how the method works. As I mentioned in this video, the standard deviations will be known. So basically the idea is this. We'll have two populations. We're going to take a sample from each population and compare those samples. So to test the difference between the means of two different populations, we need the following. The samples are randomly selected the populations are normally distributed or each sample size is at least 30. Now the notations you'll see for such a thing, you'll see notations like this. And you'll see things like this. This is basically, we consider our data to consist of x1 bar minus x2 bars. Okay, so we've got a bunch of those data statistics hanging around. All right, and we're interested in the mean of those differences or the standard deviation of those differences. But anyways, the way it works out is the following. This will come under the normal table. You'll use the normal table for our tests here. The mean is this mu of x1 bar minus x2 bar. That's all subscripted. And then one standard deviation away, let's call this one standard deviation or one error level. This distance between that one standard deviation and the mean, that is our sigma x1 minus x2 bar. This sets up a 2-sample z-test for two means. Let's call them mu1 and mu2. So what are we going to do here? Sigma 1 and sigma 2 are known. The samples are random. The samples are independent. Both populations are normally distributed, or both n1 is greater than or equal to 30 and n2 is greater than or equal to 30. That just means each of the sample sizes is at least 30. The standardized test stat is z equals x1 bar minus x2 bar minus mu1 minus mu2 all over the square root of sigma 1 over n, but 1, that sigma 1 is squared, and then we have sigma 2 is squared over n2. As you read textbooks, you'll notice that a lot of them will use this. And right there, this you'll see in whatever formulas they use. Instead of this big square root down here, they'll simply put this sigma sub x1 minus x2. No biggie, but this is the formula that we're going to use to run our tests. And now, what do these hypothesis tests look like? So here's the hypothesis test itself. Verify that sigma 1 and sigma 2 are known. The samples are random, and either the populations are normal or n1 is greater than or equal to 30 and N2 is greater than or equal to 30. Most of these things, you only will have to decide this if you're doing a real life project. For most of the problems that you have to do in this textbook, obviously, we'll state these things up front. So after all that stuff, then we have our usual business. We state H0 and HA. Specify alpha. Determine the critical values. Then we're going to use the test stat and then make the decision. I only write this out every time so that you can see that it's going to be the same steps we always do. The only difference here is the computations in the middle of them. Here I have the following claim. The claim is that mu1 is greater than mu2. And here's the information that I have. I have that sigma1 equals 40, sigma2 equals 15. Then let me get my samples down there. My samples, we have the first sample, the mean was 500, and the size of that first sample was 100. On the second sample, we had a mean of 495, and the size of that sample was 75. And we want to test the claim at alpha equals 0.10. So we'll start like I always do with the classical method. Let me first tell you that we're going to make the assumption in this problem. Well, we don't have to make any assumptions actually in this problem. I don't even have to assume the two things are normal, the populations, because each of the N1 and N2 are greater than or equal to 30, so I don't have to check anything else out. I do have to rely on the fact that these samples are random though, so we'll take that with the problem. Now, when you're setting these up, remember the strict inequality goes into H sub A. So since my inequality of the claim was strict, it goes into H sub A. So there's the claim. Now H0 always reverses the inequality and adds an equal into it. So any versions of equality are found in H0, just like before. Now the arrow, or the inequality sign right here, this inequality points to the right, so we know that we have a right-tailed test. Now, as per usual, in the classical method, let me write that first. We start with alpha, but now since it's a right-tailed test, we want the amount of area that is to the right of wherever the critical region begins. So with that in mind, we have a right-tailed test, alpha is equal to 0.1. We know that we need to take 0.5 minus 0.1 to get 0.4. That's the number I'm going to look up in the table. Let me draw a picture. These are all the normal distribution. More than just the normal distribution, this is the standard normal distribution. That means the center is at 0. And what I'm going to do, when you look up in the table, what you're trying to find is this value here. This will be called z sub 0. And you're going to try to find that knowing that this area in here is 0.4. That means that 0.1 is in that outer region. And of course, this outer region here is the critical region. So to figure out this value, I'm going to look up 0.4 in the standard normal distribution table. I have them all on my desktop. Not a bad idea for you to put them there too. Let's see if we can find the normal table. There it is. I'll zoom in as needed. I'm trying to find 0.4 in the middle of this table. Here we are. Here we have 0.3997 and 0.4015. These two values in the normal table. 0.4 is in between them, but it's closer to 0.3997, so therefore I will use 0.3997 for my area in the table lookup. So from that, then let me go across the row to 1.2, and then let me go up the column to 8. So I know that my Z naught is 1.28. So from the table, if you want to call it the standard normal distribution table, go ahead. Z naught equals 1.28. Now, you can also do this kind of a thing with your calculator. If you know that this area is 0.4, how do you use your calculator to get this Z naught value? So let's open up the calculator and let's take a look at our stats menu. So if you click second DISTR, this is for statistical distribution, we're interested in the ones that involve norm. So inverse norm means you're trying to find a Z value. Regular norm means you're trying to figure out how much area has been accumulated. So when I do this, the way you put it in here, let's go ahead and choose number 3. The area, what it wants is the area from negative infinity all the up until you get to that point. So that's actually 0.9. Since it's a standard normal table, you can use mu and sigma. And let's go ahead and press enter and see what we have. Well, keep going. It shows you the way that you are supposed to type it in. And you see it's close to the value that we got. If we go back to the thing the table gave us, the table simply rounds it to 2 decimal places, whereas your calculator is able to give you more decimals because it actually has a much more advanced table in it. I don't know if it's figuring out the mathematical computations behind the scene or if it's simply pulling information out of a table. But for whatever it's doing, your calculator will give you more decimals of accuracy than the table. Now, let's go ahead and calculate our statistic. So our test statistic looks like this. We have Z equals x1 minus x2 bar minus mu1 minus mu2 all over sigma1 squared divided by n1 plus sigma2 squared divided by n2. Let's put in all of those numbers. So my samples, my first sample had a mean of 500 and the second sample had a mean of 495. So I got 500 minus 495. Now the other part of it is sort of interesting because if you remember when we were doing our hypothesis tests, we always put the mu equals whatever it possibly was in the H naught. So what I'm trying to say, that's a very complicated way. In H naught, we are half of H naught is telling us that mu1 might be equal to mu2. That means that if I consider mu1 minus mu2, H naught said there's the possibility that those means are 0. And that's exactly what H naught is trying to do anyways. HA is trying to tell you that one's bigger than the other. H naught is trying to say, no, they're no more than equal to each other at the very worst. Now let's put our other information. This is why you need sigma1 and sigma2 to be known. Sigma1 is 40 and sigma2 is 15. So we have 40 squared over, my N1 was 100 and N2 was 75. And let's go ahead and calculate it. I get approximately 1.147. Let me take a look at the start of my rejection region. I see the 1.147. Z naught was equal to 1.28. So 1.1 anything is going to be out here in this area. Let me clear out a little bit of that so that you know that is a non-rejection region. So this tells us to fail to reject H naught. Now let me show you how to use the p-value method to do the same type of problem. So here, let me redo with p-values. Now, this time you start with this test statistic. So we have our z was equal to x1 bar minus x2 bar minus mu1 minus mu2 all over the square root of sigma1 squared divided by n1 plus sigma2 squared divided by n2. And I had put in all of our numbers up top, and this came out to be approximately 1.147. Of course, you could use more decimal places if you would like. Let me show you why that would be useful. Let me grab the calculator up here and throw in the numbers that we know. Now to do this, remember mu1 minus mu2 for these tests is usually going to be 0. So all we're going to have here is, I believe it was 500 minus 495. Yeah, let me put that so I can see what I'm typing in. So we will encase that in parentheses. 500 minus 495. And then I will finish off the parenthesis. Now I'm going to divide by the square root of a bunch of stuff. Here, I don't think it grows, but let's see what happens. My sigma1 was 40, so I'm going to do 40. Now you can do this little square and then divide it by 100 plus, and then we have the 15 squared. I see the vinculum on the square root is increasing as I type this out. So I don't need to put parentheses around all that stuff. Let me make sure I get the same number. Yes, I do. Now what I might want to do is this. Let me go to the distr, which is right above vars here. Let me click on it. This time, I don't want to know what the z value is, but I would like to know how much area is accumulated up to that point. So I'm going to use this thing, normal CDF. the 2 on there, the CDF stands for Cumulative Distribution Function. What cumulative means is it's adding up area until it gets there. So the lower, you can always, this is its way of saying negative infinity. My upper is exactly that. I don't know if it will let me do, I'm going to write second answer, because it has more decimals than I was doing before. And then for the rest of this stuff, they're the same because it's a standard normal table. It shows you how the setup is in it. And let's see what we get for area. 0.874. Now when your calculator does this, here's what it does. We had 1.147. The calculator measures the area in here. It measures the area until you get to 1.147. That is, this number here, this 0.874 that the calculator gives me, is the area from negative infinity until the cutoff point. So 0.874. Now I don't want that. This value out here is the p-value. How do I get that? Well, I subtract the 0.874 from 1. And that gives us, let's see, I can do it on the calculator. You can do this real quick. You can go -1, and it will take the answer minus that. I know it's negative, but I'm capable of dealing with that. I get 0.126. Now, the p-value is 0.126, but alpha equals 0.1, so you can see that p is greater than alpha, which implies that we fail to reject h sub 0. All right, here is an example from the current textbook we're using. The textbook tells me that we are to assume that these populations are normally distributed, so I don't have to worry about all that business, and that the samples are random, and that they're independent. Well, I think you can determine if they're independent, since there are two types of washing machines. Unless one is an older model of the other one, I'm assuming there are two completely different types of washing machines. And we're comparing their mean repair bills for each of the machines. So let's take a look at what we have then. Let's look at Model A. All right, what do we have for Model A? We have the number in A, I'm going to call it N sub A, was equal to 24. So there's 24 of these machines. The mean repair, so the mean of A was equal to $208. And then I just made a mistake when I wrote that. And then what else do we need? I need the standard deviation for Model A's. The population standard deviation is $18. So sigma A equals 18. For Model B, we have the number in that sample was 26. The mean of that sample was 221, and the standard deviation of that population is 22. So now they're trying to determine, well, let's first see what the question is asking us for. So let's write our claim down. So the salesperson, a salesperson tells you that the mean repair costs for Model A and Model B are equal. So the claim is that mu A is equal to mu B. And then we're going to test the claim at alpha equals 0.01. And as usual, I'll do the example two ways, one using the classical method and one using p-values. You can decide on which one you like better. So let's first get my H0 and my HA. Well, H0 is simple. That's the one with the equals. This is actually the claim as well. You don't have to write the word claim, though it's very useful, I think. So then our other one will be not equal to. So this is a two-tailed test. That means I'm going to have a positive Z0 value and a negative Z0 value. The same thing as before, alpha equals 0.01, but since I'm using a two-tailed test, I need to divide these in two. So that is 0.005. So now let me use the table to get the Z0 value that starts that region. Remember, in order to make use of the table, I need to do 0.5 minus 0.005, and that equals 0.495. Let me go to the standard normal table, and it should be here still. So I would like to 0.495. I'm getting there. Halfway between values, exactly halfway. 0.4949, 0.4951. So let me go across. That's 2.5 between 7 and 8, but if it's an equal amount, you're supposed to do 2.57 and then throw a 5 on. And remember, since it's a two-tailed test, you can do plus and minus. If, on the other hand, you wanted to use your calculator to come up with at least one of these numbers, you have to still think and use a positive and negative. But you may not have to. Let's go back to our table and see if we can remember how to do this. So once again, I'll go back to the blue thing above vars, which is DISTR. And what I want now, right now I want to use inverse norm, that's number 3, because I'm going to feed it in an area. I'm not going to feed it 0.495, I'm going to feed it 0.995 because it takes the area from negative infinity all the way up until you get to z sub 0. So let me choose 3 for my inverse norm. You can see it does some idiotic things. It's just the nature of either this or the calculator. Let me put my 0.995. Of course, since it's a standard normal distribution, mu is 0 and sigma is 1. Let me enter my way out. This just tells you what to put, and then let's see what we have. I get 2.57. If I stop at 3 decimal places, my calculator gives me Z0 will equal plus and minus 2.576. So you see, the table is not far off from what the true answers are. So what do I have? Let me draw a picture. Let's see, I've got 2.575, and then I've got negative 2.575, or 6, whatever it is you want to use. These are our rejection regions. And now let's take a look at my test stat. Z equals x1 bar minus x2 bar minus mu1 minus mu2, which is going to be 0, divided by the square root of sigma 1 squared over n1 plus sigma 2 squared over n2 And let's go ahead and put in our numbers. And I have switched. My notation had A's and B's, but now I changed them to 1s and 2s. I think I should be consistent with my notation. The reason I'm mentioning this is you'll find that the notation can help you quite a bit as you do these problems. So I'm purposely not subtracting or erasing this part because I wanted you to see. Make sure, though, you keep everything in order. Now, in the denominator, inside of the square root, none of that stuff matters. If you're in order or not, it'll commute. Now, I just noticed that when I started to put in my numbers, I'm calling them sub A's and B's. So let's take a look at what we have. X A bar is 208 and X B bar is 221. So we got 208 minus 221 minus mu. The H naught tells us that mu1 might possibly equal mu2. And then let me get my sigmas. Sigma is 18 and sigma b is 22. And let me get my NA and NB. Where did you go, NA and NB? 24 and 26. And let's see what we get. So I'll bring this up to the calculator. And once again, the way to do it on here is you're going to want to put in parentheses this part, 208 minus 221. I do need parentheses around there so that it knows that the entire thing is in the numerator. And then let me get my stretching square root. We're going to have 18 squared divided by 24 plus 22 squared divided by 26, and then I'll hit enter and see what we get. Negative 2.294. And if I look at the rejection regions, negative 2.294 looks like it's in this area here, so we fail to reject H naught. Now, to do the same problem with p values, you start with the test statistic. So we have z equals negative 2.294. And then your calculator, you want the calculator to give you the amount of area that has occurred up to that point, from negative infinity up to that point. So what do we use? Let's go to second, and then above bars we see the distr. If I want area, that's this guy right here, number 2, normal CDF. So let me click it. The negative infinity up to the little minus down here is what you got to use for negative. 2.294, and everything else stays the same. Here I get 0.0109. So remember though, this is a two-tailed test. So what the calculator is giving us is that 1/2 of p equals the number that I just quoted you. I don't need a huge amount of decimal places, so I'll just grab a few. 0.0109, I'll go with that. That's because this also works a little bit like that. This is the amount of area to the left of that, but since it's a right-tailed test, there's also, on the positive version of this thing, this number, there's that amount of area to the right. So remember, you've got to multiply this by 2. P then will equal twice that number. So let me have the calculator back and multiply that by 2. So I get 0.218. Now, in this whole thing, what was the alpha to begin with? You don't have to split alpha up here. The original alpha was 0.01. So we have that P is greater than alpha, so this implies that we fail to reject H sub 0. Here's another example. This is the last example for this particular topic. We have, let me put down the information we have. We have 2 samples. So sample 1, we had 120 students with a mean of 20.1. So we have X1. Oh, that was the English score, so let's use X sub E was 20.1, and then N sub E was 120, and then the standard deviation of that first sample was 6.8, so sigma sub E was equal to 6.8, and now sample 2. Here, for the other one, was a reading score. So X, for the reading score, the mean was 21.3. So let's call this X sub R. That was 21.3. N sub R, what was that? That was 150. And sigma sub R was equal to 6.5. And what is going on here? Can you support the claim? So the claim that ACT reading scores are higher than ACT English scores. So we want the claim is that the English scores are, well, we could do this. I could say the English scores are less than the reading scores. Since my sample 1, the E, was first and sample 2 was that, I decided to write it like this. I could have written mu R is greater than mu E, but then the other stuff would have been in the wrong order. So I want to keep things in the correct order here, and I have that. All right, well, let's go ahead and test the claim at alpha equals 0.10. So as usual, I'll start with the classical method first. Let me get these things down. So our claim is that mu E is less than mu R. So I'm going to put mu E is less than mu R. That'll be in the alternative hypothesis. That means for the other hypothesis, I switch and equate mu E is greater than or equal to mu R. So down here, this is pointing to the left, tells me that we have a left-tailed test. So let's go ahead and then calculate our Z0. Our alpha equals 0.1. Now to use the Z table, I need to do 0.5 minus 0.1 equals 0.4. And from this, I can use the z table to tell me what the z0 value is. And remember, since it's a left-tailed test, this will be a negative number. So let me have my table. 0.4. It seems like we just looked this up. No. We came up with 1.28 because it's closer to 0.3997 than to 0.4015. So since it's closer to 0.3997, I will use 1.28, which means in here I will use negative 1.28. Draw a picture to help if you need. And here is our rejection region. Let's calculate our test statistic. That's z equals x1 bar. Well, I'm not using ones and twos. I'm using e minus x bar for reading minus mu e minus mu r divided by sigma e squared all over ne plus sigma r squared all over nr. And let's get all of those numbers. Alright, I need my samples now. Where are my samples? 20.1 and 21.3. So 20.1, 21.3 minus, and the other part is 0 almost always. Down here, let's see what my sigma and n's were. So 6.8, 120. And then the other one was 6.5 and 150. And let's see what the calculator gives us. Don't forget to encase the numerator in parentheses, or this will not work out right. Now the square root is nice enough to extend the over bar to, it grows as you type in the expression, so that's very, very useful. I don't need to have extra parentheses in the denominator. I get negative 1.469. Let's see, that is most definitely in the rejection region. Right there it is. So we reject H sub 0. Now let me reproduce this with p-values. And so, as before, you start with the z statistic. So z was equal to negative 1.469. And now I'm interested in finding out how much area goes from negative infinity up to that point. So what you want is the cumulative distribution function. So let's go ahead and grab our calculator. Second, DISTR. And I'm looking for number 2 for the normal CDF. The lower's what I want, good. Negative, that's its version of negative infinity. Then we have negative 1.469, and you can use as many decimal places as you want. You'll just get more accuracy the more places you go. Gotta click my way out of this thing. And it looks like we have 0.0 0.709. Well, if you recall from the first part, alpha was equal to 0.1, and here we have a situation where P is definitely less than alpha, so we reject H naught.